my previous lecture I was discussing about the how to write the first law for a process taking place across a control volume when the control volume undertakes or undergoes an unsteady process. And eventually we came to a special case of this unsteady state evolution of a control volume, which is uniform state uniform flow process or USUF process. So, today we will work out a few problems to illustrate these USUF concept. So, the first is the transient the first in the transient problem list is problem 4.9. Okay. So, this problem 4.9, this is a very classical problem. This is called as a tank filling problem, you know. So, what is a tank filling problem? There is a tank which is a 25 liter tank shown in the figure that is initially evacuated. It is connected by a valve to an air supply line flowing air at 20 degree centigrade 800 kilopascal. The valve is opened and air flows into the tank until the pressure reaches 600 kilopascal. Determine the final temperature and mass inside the tank assuming the process is adiabatic. So, in the process develop an expression for the relationship between the line temperature and final temperature assuming that the specific heats are constant, that is calorically perfect gas. Okay. So, we will work out the problem as we have done for all the problems in the previous chapters. We will draw a schematic of the problem and give you a outline of how to solve the problem in the board. So, you have a tank, this tank and there is a air supply line. So, this is a pipe which supplies air, air is moving like this. When this, so initially this tank is empty and this valve is closed. When this valve opens, the air from the air supply line enters and fills the tank. This is what as I called earlier as tank filling problem. So, this tank is insulated. Typically for insulated chambers, this is how we draw symbols. So, this shows that it is insulated. Let us write what is given. So, V is 25 liter, which is the volume of the tank. It is initially evacuated, that means M1 is 0. Mass within the tank, which is the control volume. So, let us draw a control volume here. Okay. So, this is there, mass 1 is 0, then air supply line. So, this is the inlet I, state I, the air supply line is Ti is 20 degree centigrade and Pi is 800 kilopascal. Process is adiabatic. So, heat transfer is 0. So, this is like normally, I mean from my own student life I used to do this, that whatever is given as a data somewhere write it, so that it gives you a clarity of what is known and what needs to be found out, because based on that only you will apply the relevant equations. So, I mean maybe all these data may not be necessary for problem solving, but whatever is given you list it somewhere. So, so this is what is given, and this tank has only one inlet and no exit. So, there is no ME, right, that also needs to be kept in mind. So, there are 4 states associated with this unsteady process I, E, 1, 2. So, as per the symbols we have used for our derivations, the differences between these 4 should be absolutely clear to you. I inlet, E exit, 1 initial state of the control volume and 2 final state of the control volume. So, we have to associate all these states. So, I is there, E is 0, 1 is 0 and 2 you have to figure out that what is the state 2, that is the whole problem. So, let us write the mass balance. So, M2 minus, so Mi minus Me is equal to M2 minus M1, right. So, here M1 is 0, Me is 0. So, M2 is equal to Mi. This is so common sense that initially no mass was there. So, final mass inside is same as whatever mass has come in. So, you really do not need to do it that elaborately, but I am trying to give you a structure to the problem solving, so that how you use the fundamental equations to arrive at your final thing. So, energy balance Q plus this So, if you have a feel of what you are writing, this you do not actually have to memorize. This is energy balance. So, you can write energy balance without memorizing the formula. Okay. So, now let us simplify this equation based on what is given. So, first of all M1 is 0. So, because M1 is 0, this term will be totally 0. Then Me is 0. So, this term is totally 0. In this problem, what is neglected is the change in kinetic energy and potential energy, because here the main problem associated is the transfer of thermal energy, not so much kinetic and potential energy. So, kinetic energy anyway this term is 0, but for the other terms kinetic energy and potential energy, even for any term you can write, the changes are not important. On the top of that, you know, because it is insulated, the heat transfer is 0, and because it is a rigid tank, there is no system boundary displacement and there is no other form of work that is extracted from this device. So, this is 0. So, you are left with a very simple equation, MIHI is equal to M2 U2, right. And from this equation you know already from mass balance that Mi equal to M2. So, U2 is equal to Hi. Okay. Now, further assumption that is given in the problem, that you can treat this air as an ideal gas with constant CpCv. So, right. So, T2 is equal to Cp naught by Cv naught, Cp naught, Cv naught are CpCv corresponding to a constant CpCv of ideal gas. So, T2 is nothing but Ti into the ratio of specific heat Cp and Cv, which is often called as gamma. So, the final answer is T2 is equal to gamma Ti. So, very interesting, you see, try to understand the physics of this problem, then you will appreciate this problem more. So, you have a tank, there is a line which is filling up the tank, the temperature inside the tank is always greater than the temperature in the line, because Cp is always greater than Cv. Why? The reason is that to penetrate this fluid into the tank, an additional energy beyond the internal energy had to be there, because it has to maintain the flow in presence of pressure, and that is flow energy or flow work. So, because in addition to the internal energy, the flow energy is also coming into the tank, that makes the tank energized in a manner so that its temperature eventually is greater than the temperature here, because when the fluid is inside the tank, the entire flow energy gets converted into internal energy. The internal energy here plus flow energy here, this total energy gets converted into internal energy within the tank, and that makes the temperature, you know, shoot up from the temperature here. So, this is the physics of the problem. The other important point that I intend to make is that, you know, when we think of state I, the inlet, can we take it here or can we take it here? Is there any difference? See, for problem solving purpose there is no difference. Why? Because eventually for the state I we require only the enthalpy, right, and enthalpy, this is a throttle valve. So, enthalpy before throttling is same as enthalpy after throttling, right, with all those assumptions that we had earlier discussed. So, that makes this problem solving absolutely alright, no matter whether you take I here or here, but when you take I here you incur those additional assumptions that make sure that enthalpy here is same as enthalpy here, because that is based on some approximation, but those assumptions are valid for most of the practical problems. Okay. So, the answer to this problem is 410.5 Kelvin. Remember that when you write a relation like this, the temperature has to be in Kelvin on both sides. Okay. So, let me erase the board and then we will move on to the next problem. Problem 4. The problem number 10. A 100-liter rigid tank contains carbon dioxide at 1 MPa 300 Kelvin. A valve is kept cracked open and carbon dioxide escapes slowly until the tank pressure has dropped to 500 kPa. At this point the valve is closed. The gas remaining inside the tank may be assumed to have undergone a polytropic process, polytropic expansion with the polytropic exponent n is equal to 1.15. Find the final mass inside and heat transferred into the tank during the process. So, to summarize, this problem is a tank emptying problem instead of a tank filling problem. So, in the previous problem fluid was filling up the tank, in this problem fluid is leaving the tank. So, let us try to draw a schematic and as the previous problem try to identify the relevant properties. So, this is your control volume and you have a state E . So, the fluid is carbon dioxide, state 1, 1 MPa 300 Kelvin, state 2 500 kPa, between state 1 and 2 you have a polytropic process which is defined as PV to the power n equal to constant. Remember, polytropic is not, polytropic is a generalization of all processes, because you know if you put n equal to gamma which is the ratio of Cp by Cv, then it is a special type of adiabatic process which is called as reversible adiabatic process. We will learn this later on. When n is equal to 0, so that means P equal to constant. So, it is a isobaric process. Similarly, there will be cases when n is equal to 1, then PV equal to constant. So, that is called as reversible isothermal process, and then you can also have V equal to constant as a part of this process. So, you can write V equal to C into P to the power minus n. Okay. So, you can set what value of n, you think about this to make sure that V is constant. So, that is called as isochronic process. So, different types of processes can be modeled. This is a model, remember. The value of n will dictate what is the physical process. So, in this case, yes.
I think it is P into specific volume to the power of n in this question, because
in this question, yes, you are correct. In this question it is P into specific volume to the power n. But you know always we write its specific volume just to recognize that it is for a given mass of gas. So, to make sure that the mass reference is same. So, why this is important? In this case state 1 and state 2 will have different mass. So, to rationalize with respect to a given mass, if you write the change, then it is specific volume instead of total volume. In case for a control mass system, it does not make any difference. Instead, in case of this particular case where the mass in the control volume is changing with time, this is what is more appropriate. So, now state 2 temperature you do not know, but what you know that you have P1 V1 by T1 is equal to P2 V2 by T2. This is also on a mass basis, given mass, right. So, P1 by T1 is equal to P2 by T2 into V2 by V1. So, you can write P1 V1 to the power n is equal to P2 V2 to the power n. So, that means this into V2 by V1. So, V2 by V1 is equal to P1 by P2 to the power 1 by n, right. Right. So, now you can simplify this and write. So, T2 by T1 is equal to P2 by P1 to the power n minus 1 by n, right. So, then this is T1, this is P1, this is P2. So, you can calculate what is T2 from here. So, T2 is 274 Kelvin. Okay. So, M1, now you use this one, this is total volume, because you want to get the mass. This R is not universal constant, it is universal constant by molecular weight. So, universal constant divided by molecular weight of carbon dioxide. So, this you can calculate, because you have V1 as 100 liter, which is same as V2, P1 you know, then R for carbon dioxide you can find out, and T1 is given 300 Kelvin. So, you know what is M1. R of carbon dioxide, just for your reference I am giving you this value 0.18892 kilojoule per kg Kelvin. Okay. So, then you can also calculate what is M2. Okay. So, this you can find out. So, now you can use the first law. So, first law, so for mass balance, ME minus MI is equal to M2 minus M1, right. So, here you have MI is equal to 0, there is no I. So, ME is M2 minus M1, M2 M1 you know. So, you know what is ME. Then you come to first law for US UF. So, Q plus MI into whatever, here MI is 0. So, I am not interested about that. So, M2 into U2 plus V2 square by 2 plus GZ2 minus M1 into U1 plus V1 square by 2 plus GZ1 plus ME into HE plus V square by 2 plus GZE plus W. Okay. So, then again a rigid tank, there is no W, but it is not an insulated tank anymore. So, there is heat transfer, in fact that is the question, find the heat transfer to the tank during the process. So, then this term is 0, we neglect changes in kinetic energy and potential energy. So, you have M2, M1 all these known, and then you have ME also from this equation you know. You know U2 and U1 because state 2 and state 1 are already known. Assuming ideal gas, they will be functions of temperature only. So, given the temperature 300 Kelvin and state 2 this 274 Kelvin, you can find out their internal energies. There is a critical part of this problem, that what is HE? See, the state E is the exit state, but you know this continuously changes as the gas is leaving. So, how do you assess it? So, essentially a good approximation to this, remember this is what engineers commonly do. If we do not have an exact idea of the picture, we give an approximation to that. So, what is the approximation? So, this is roughly like HE at T1 plus HE at T2 by 2 roughly, where T1 is 300 Kelvin, T2 is 274 Kelvin. The state E is continuously changing as that you know state in the tank changes from 300 Kelvin to 274 Kelvin. So, E is no more a fixed state which we assumed as a part of our derivation. So, here there is a conflict between this the derivation of this equation and the physical situation. To resolve that conflict or paradox, this is what we are assuming. So, this assumption is very very important, you know, otherwise you cannot solve this problem with a practical outlook, and if you do that, and then for you know U and H you can use constant CPCV. So, you can assume Cp0 is equal to 0.8418 this kilojoule per kg Kelvin, and Cv0 is equal to 0.6529. So, if you consider this, then you will get the heat transfer Q is equal to 20.1 kilojoule. Okay. So, why do you require a heat transfer to the tank in this problem? See, whatever energy was in the tank is trying to carry more energy out of it because the flow energy is also going out. So, to compensate for that additional loss of energy, a heat has to be transferred. Okay. So, let us stop here for the time being. We will continue with more problem solving in the next lecture.